we have Professor Narayan Banerjee from IISER Kolkata speaking about the Raychaudhuri equations, its genesis and significance. Professor Narayan Banerjee had done his PhD. He's a grand student of Professor Raychaudhuri, and he had done his PhD at Jadavpur, where Professor Raychaudhuri used to visit regularly, as was mentioned by Professor Sudipta Das yesterday. And he has had many close interactions with him. And Professor Narayan Banerjee has worked on a variety of aspects of gravitation and cosmology. Of late, he has been largely working on issues related to dark energy. And today, as I mentioned, he'll be talking to us about the Raychaudhuri equation.
And I should also thank and congratulate the organizers, Dhiraj, Arnob, Manjuri, and Ravindran, for organizing such a nice meeting on the occasion of AKR's birth centenary. So on behalf of perhaps all the speakers, I should say, because this is the last academic business of this meeting, on behalf of all the speakers and participants, I would like to thank all of you. So I shall be talking about Raychaudhuri equation, for which AKR was famous and for which we have gathered here. But today's program is meant for undergraduate students. So believe it or not, there will be nothing in store for an expert of the field. There will be nothing for them. So there will be some equations, of course, but I shall try to explain all the terms. You don't have to concentrate much on the equations, but I hope you will understand something out of it. So Amol Kumar Raychaudhuri, popularly known as AKR, was one of the doyens of Indian relativity research. As Pankaj has mentioned, we all grew up looking at Professor A.K. Raychaudhuri and Professor P.C. Vaidya, and they were father figures for all of us, and inspired. They always the one thing in common they had. They always inspired younger researchers. He was internationally reputed scientist, contributed significantly in understanding of modern cosmology and also black hole physics. We have come to know some of that from Shoumitra's talk and Pankaj's talk. The year 14 September 2022 to 13 September 2023 was his centenary year. So we're very close to the centenary year, so we are celebrating that. So his discovery was Raychaudhuri equation, is an outstanding contribution to knowledge, and we shall come to that. But we shall start from something else. We shall start from a bit of cosmology in a very popular way. So cosmology, you know, is the science of the universe. I mean, it discusses its birth and evolution of the universe. It contains whatever we can see now, we have seen in the past, and we expect to see in any foreseeable future, with see meaning observe in any way, with the finest of our instruments. That is all constitute our cosmology. Building blocks of the universe are the galaxies. A typical galaxy contains about 10 to the 11 to 10 to the 10 to 10 to the 11 stars. And the typical linear size of a galaxy is around 10 to the 5 light years. So you can see how big it is. But and the typical distance between two neighboring galaxies is around 10 to the 6 light years. And these galaxies are the building blocks of the universe. So you know what scale we are talking about. So Hubble in 1929 discovered that these galaxies are all moving away from each other. So if we look back in the past, so they were closer together. If we look farther back, they were even closer together. In this way, we reach a point when they were all together. So you can well imagine, even I cannot place this pen and this pointer at the same point. So it had a different kind of distribution of matter. It was all in the form of energy, as we all know. Matter and energy are the same thing, different manifestations of the same physical object. So we had an infinite density and a zero volume, which is called a singularity, in a popular way, We shall talk about the singularity in a more, technical way later. So anyway, this universe, so Hubble's discovery reveals another thing. The universe, as was believed in the past, remained the same throughout the history. It's not like that, it's evolving. So it's interesting as a physical subject. So that was also established by this observation. And it started from a very bad shape, from a singularity of infinite density and zero volume. So as the universe is now physically interesting, an interesting subject to be dealt with in physics, so we have to model it. We have to predict certain things. So for modeling the universe, we have these three basic assumptions. One is the universe is spatially homogeneous and isotropic, meaning that everywhere the distribution of galaxies is the same, and they're same in all directions. Isotropic meaning same in all directions, homogeneous means same at all points. You can straight away ask, this is not true. You said that a galaxy is around 10 to the 5 light years long, and another galaxy which is situated, the closest galaxy is situated some 10 to the 6 light years away from that. So in between there is nothing. So it's matter, void, like that. So how you can say that the universe is homogeneous or like that? So think about the scale that we are talking about. So we learned about kinetic theory and gases in our first year undergraduate, where we know that suppose you say that the gas is uniform. The gas in a given container is uniform. But you know that the size of the molecule is much smaller compared to the mean free path. So how can you say that is uniform? So you have a very high density site of the molecule and nothing, and another molecule and nothing in between that. So, but if you pick up a cubic centimeter, a cc of volume from any portion of the container, you will find the number of molecules are the same. Some are going out, some are coming in, but on the average, the number of molecules will be the same. In the same way, if you think about a sphere of, let's say, 10 to the power 8 light years, if you pick up the sphere at any part of the universe, the number of galaxies will be roughly the same. So this is an observational fact that the universe is homogeneous, and also in all directions. Not only homogeneous, but also isotropic. But what is the matter distribution in the universe? So I said this is a galaxy, they are the galaxies. But the galaxies are distributed through the universe in the form of a fluid. So that is another assumption. This is called hydrodynamic approximation of the distribution of matter in the universe. Number three, so we know about the interactions that we see all around, the strong, weak, electromagnetic, and gravity. Gravity is by far the weakest, but gravity is the interaction which that governs the dynamics of the universe. Strong and weak forces, they are very short range, and electromagnetic interaction doesn't help because the universe is found to be neutral on the average. So these are the assumptions. Inspired by the, So now we are ready to model the universe. I first talk about general relativity, which is believed to be the correct theory of gravity. Okay? So what general relativity is all about? So we all know about the special theory of relativity that we can assume because we are already in the undergraduate classes where we know that that the laws of physics will be invariant in all inertial frames and things like that. So inspired by the success of that, Einstein wanted to have a generalized theory of relativity, where the laws of physics will be valid not only in an inertial frame, but in all frames, including accelerated frames as well. So these are the two postulates. Laws of physics are invariant in all frames. This is called the principle of general covariance. But while doing that, Einstein also discovered, I'm not getting into the details of that, gravity is equivalent to an accelerated frame, which is called the principle of equivalence. Where does it come from? Simple. It comes from the, let's say Newton's law, force is equal to mass times acceleration. But for gravity, we know that the acceleration is, the force is minus g m by r cube times r vector, inverse square. Okay. So now you see that small m is the mass of the particle, that motion of which we are interested in. So the trajectory of the particle, the acceleration does not depend on the mass of the particle. That gives some uniqueness of the of gravity. Let us think about a thought experiment. Suppose we are in a spaceship and we are coasting along. We have crossed the gravitational field of the Earth, and we have not entered into the gravitational field of anything else, but we are coasting along. So there is no gravity. So if the astronauts A, B, they are moving around all around the spaceship. They're not standing on their feet. They can move along anywhere in the spaceship. Now suppose it was engineered like that the spaceship at some point of time starts accelerating. So against the direction of acceleration, the astronauts are now standing on their feet. So they have a floor and ceiling and walls. Before that, they were not having that. All were walls. There was no floor and neither any ceiling. Now, if they have a ball in their hand, if one of them, he drops it, it falls. So he says to his partners, look, we are almost in our home. There is gravity. But his partner said, well, you can see that you can see the time. So we are now accelerating. So the first astronaut says, yes, you are right. But then he says, how is it different? So Einstein picked up that. He said that the accelerated frame and gravity can be replaced by each other. So these are the two postulates of general relativity. But you see, gravity can be replaced by accelerated frame. That's very good to learn. But gravity has its social responsibilities. So that I am talking to you in a very gentlemanly manner, standing on my feet here on the stage, is because of gravity. So how to realize that? So Einstein said that, well, in the presence of gravity, the space-time around a matter distribution will be curved, and the test particles will follow the trajectories determined by the space-time. It's somewhat like, again, this is the first time I am going to AKR. So when he taught general relativity on the first day, he gave us this analog. He said, suppose you go to a railway station and ask a mathematician, so what will be the trajectory of the train? The mathematician will say, it's not difficult. I know the force equation. Force is equal to mass times acceleration. So give me the force and give me the mass of the train. I shall give you the trajectory. But mind you, that is a second order differential equation. So don't forget to give me 2 initial conditions. In fact, 6 initial conditions. It's a 3-dimensional field, force. So force is a vector, 3 dimensions. So give me 6 initial conditions. I shall solve 3 second order differential equations and give you the trajectory. So you will think that, oh, this mathematician knows so many things. But if you ask a porter, what will be the trajectory of the train car? He will say that the rail lines are there, that is the trajectory. So the idea of general relativity is to lay the train lines there in the space-time, and the test particles will follow that trajectory. So that is the idea. But as you know, the train lines, laying the train lines is not an easy job. So finding the trajectory is also not an easy job. But once you do that, you are through. So how to do that? So Einstein says that, well, so as the trajectory is a part of geometry, and what gives you gravity? Matter gives you gravity. Matter and geometry should be related, and they are related by this equation, g mu nu is equal to minus 8 pi g t mu nu. You don't have to think of this very seriously. Geometry is g mu nu, capital G mu nu, and t mu nu is matter. So, and so this is a second order differential equation again, and you have to solve for some quantities called small g mu nus. I shall come to that what it is. And this is a second order differential equation involving these g mu nus, small g mu nus, okay. Yeah. Yeah. So, sorry. So, okay, I shall come back to some more technical things later, but I should also tell you about some success stories of general relativity. As a theory, it's a nice theory. You can say that everything is a part of, gravity is a part of space-time geometry and nothing else. It's fine. But why should we do that? We are fine with Newtonian gravity, but why should we do general relativity? There are some success stories, great success stories. First, Soumitra talked about this perihelion shift of Mercury. A planet rotates around its sun, and the ellipse of the rotation, that also evolves, that also rotates. And this rotation can be explained for Mercury. The rotation, most of the rotation part of this perihelion is the shortest distance between the planet and the sun, which is at one of the foci. So this object, the perihelion rotates, and this rotation of the perihelion was explained, most of that can be explained by solar oblateness, let's say of Mercury. But some 43 seconds per century of the year was left unexplained. With general relativity, we could explain exactly that. So that is the explanation of already known puzzle. But furthermore, general relativity predicted two new things. They were also later experimentally verified, observationally verified. One is that the light rays will bend around a massive star. Let's say if some light rays come close to the surface of the sun, it will bend. And the amount of bending is close to 2 seconds of an arc, as predicted by general relativity, due to sun. During one of the total solar eclipse in 1915, this general relativity was given by Einstein. In 1919, Eddington and his team went to Cordoba in Argentina to observe the light rays during a total solar eclipse, and they found exactly that. I mean, there are long stories. There had to do some correction things and things like that. But qualitatively, they proved that Einstein was right. So there is a small anecdote. Apparently, Einstein told people, his friends, that even if they do not find it, I know that my theory is correct. But after they found it, so I don't give any importance to this observation, but actually he gave. After they found the light bending, he wrote to his mother, they have proved that I am right. So, and the second thing is the gravitational redshift. We all know about the Doppler shift. When there is a relative motion between the source and the observer, there is a change in frequency or wavelength, right? If they recede away from each other, there is a redshift. That is, the wavelength becomes longer. Frequency, so frequency becomes shorter. This general theory of relativity predicted that even for stationary objects, there can be a redshift due to the presence of gravity. That is, gravity can reduce the energy of the photons as well. This was also observed later. So with this, we can go to some cosmology, Hubble's observation. So with the assumption that there will be some equations, but I shall not insist to you that you have to understand these equations. So Soumitra told you that The distance between square of the distance between two infinitesimally separated points is a homogeneous quadratic in coordinate differentials. So that is written with the difference that now there is a coefficient which is not constant. So only thing to pick up from the first equation is A, which is called the scale factor of the universe, which gives you roughly the size of the universe or the distance between 2 points. So this is from the homogeneity and isotropy. Matter distribution, again, you don't have to read the equation very carefully, but just to note 2 things. 2 important fluid characteristics are there. One is pressure, the other is density. And the third is the equation that I wrote, Einstein's equation. So with these equations, I can write down these 2 equations, which are called Einstein's equations for the homogeneous and isotropic cosmology. And these are much more simple. A dot means time derivative. So one single dot is a single derivative, a double dot is a double derivative. So from these 2 equations and the equation of state for the fluid, with these 3 equations you can solve the system of equations. And you will find that A, the scale factor, is somewhat like for any reasonable equation of state where P is equal to alpha into rho, where alpha is less than equal to 0, greater than equal to 0 but less than equal to 1. So you can see that at some t is equal to t0, which we shall henceforth call t0 is equal to 0, the scale factor is 0. Given that is the length scale of the universe will be 0, so the volume, which is actually a cube, will also be 0 at some finite past, namely t is equal to t0. So there is no escape from this singularity. In geometrical terms, the trajectories that we said that general relativity will said that the particle trajectories will be determined by the geometry. The trajectories will all focus at a point and cannot go past that point. So this is called the geodesic incompleteness, which is the geometric definition of the singularity, the geodesic incompleteness. 2 geodesics. What are the geodesics? If only gravity is present, the line along which, the trajectory along which a material particle will flow. Okay. So the singularity is inevitable. We can now see. So AKR in 1950s was thinking about this singularity. Now I am slowly coming to Raychaudhuri equation, but I shall go back to cosmology once again. I mean, this is cosmology as well. His main concern is the cosmological singularity generic. His aim was to find out a non-singular solution for the cosmological models. So you can see that Hubble's observation, and we also found that the theory also gave us the same result. There is no escape from the singularity. Incidentally, I should make another comment that theory in fact came, the model in fact came before Hubble had his discovery. The theoretical model came in 1922, whereas Hubble discovered that the galaxies are moving away from each other in 1929. So Raychaudhuri in 1950s was thinking about the singularity, and his idea was this cannot be that. Because singularities are bad things, so there should be some non-singular solutions. So how can we escape from this embarrassment? There can be 2 options. One is that the zero volume, as I said, zero volume of the universe was reached at an infinite past. So whatever big that T0 would have been, but if it is finite, Soumitra mentioned it is around 14 giga-years. So, but it's finite, measurable. If it is an infinite past, we don't have to bother about it. There is no singularity practically. So this is one way, but we found that the theoretical model says that no. it was at a finite past. And two, if there was a minimum of the volume. That is, suppose we have a function which, if we look back in the past, it goes down and at some point reach a minimum and increases again. So there's a minimum of the volume. In that way, we can avoid the singularity. So look at it in a bit more general way. So I wrote down Einstein's equations. Sorry. Sriram taught me, I am a very bad student, I see how to go about, but yeah. Yeah, these two equations. Now you can combine these two equations to arrive at this equation, A double dot, meaning the second derivative of the scale factor, is equal to minus 4 pi g over 3 into rho plus 3p, where rho is the density of the fluid and p is the pressure. And you can well imagine that the density and pressure of a fluid cannot be negative. So A double dot is negative definite. A is the scale factor, cannot be negative. 4 pi g, 3, nothing can be negative. So A double dot must be negative, right? So if we know if there is a minimum of volume, at the minimum, the first derivative will have to be 0 and the second derivative will have to be positive. So there is no minimum of volume. So there is no way out of this singularity. For any matter distribution, this is the key equation. And yeah. So, and rho plus 3p greater than or equal to 0 is called the energy condition. We shall come back to that once again. So it's called the energy condition. With proper energy condition, we always have this minimum. Now the AKR asks this question, is the singularity an artifact of the high degree of symmetry that we have assumed? That is, we have assumed homogeneity and isotropy. The universe is same everywhere and in all directions. Is it an artifact of that? If we are ready to give up these assumptions, can we have a non-singular solution? He tried to find some non-singular solutions, but he failed. But in what ways this departure from this high degree of symmetry can appear for a general kind of space-time? And does this departure from symmetry have any role to play in avoiding the singularity? These questions was asked. So now we shall generalize this equation that we wrote. Now what we are interested in? We are interested in the trajectories. As we are talking about geometry and the trajectory of a particle, we are interested in the velocity vector of a particle, right? So out of this velocity vector, we can construct many things. So we can construct, with the velocity vector and its derivatives. First derivative, like that. First derivative will give you the acceleration in general. You have to project the acceleration in the time direction. So the velocity vector is called a time-like vector because it will give the velocity of a time-like vector, meaning, or a time-like particle will mean particle with a mass, like you, me, electron, proton, moon, and the sun. So in terms of combinations of its derivatives, we can form some quantities which can indicate how we can depart from the high degree of symmetry. But the derivatives are in a tensorial way. So there will be some tensor notations, but don't be afraid of that. Again, you don't have to be seriously thinking about that. I shall explain every term. Time-like velocity vector, I have explained what does it mean. So its derivative meaning derivative in the tensorial way. So there is a symbol of semicolon. Don't have to think about it very seriously. So, but you can easily see that this is a two-index object. You can form a matrix out of it. The trace of this will give the acceleration. Sorry, give the expansion scalar, which is scalar. Scalar object called the expansion scalar, which also Soumitra talked about. And there are two other things. So this expansion scalar is nothing but the fractional rate of increase of the volume against proper time, against time actually. The trace-free part forms shear and rotation. So this is the trace, and the trace-free part form two other objects. One is shear and the other is rotation. I shall come to that. So another important quantity is the projection of the derivative v mu, semicolon nu, that is the tensorial derivative of the velocity vector, and project it along the time direction. As velocity vector itself is the time-like vector, project it along the velocity vector and get something called an acceleration vector. So that gives you the acceleration. Now we have four things. One is the expansion scalar, which is always there even for a homogeneous and isotropic space-time. And there are other things. If there is a distortion of shape, you don't, again, I have written the equation for the sake of completeness, but don't have to think about it seriously. So if the universe is not isotropic, there is a distortion of shape. Everywhere it does not look the same. In all directions it doesn't look the same. Then we have something called a shear. Sigma square is the measure of the shear. Forget about the tensorial equation. Okay. And if there is a rotation in the space-time, this is also a kind of an anisotropy, but anisotropy involving time coordinate. But if there is a rotation in the space-time, you know what is known as a velocity vector, an angular velocity or angular momentum. So this omega is kind of an angular velocity, which is basically the curl of the velocity vector. So in an antisymmetric thing. So omega square is a square of the measure of the rotation. So these two things we have found out. Sigma, the shear arises out of the symmetric part of the trace-free part of the matrix, and rotation comes from the antisymmetric part of the matrix. Okay. So yeah. So another thing. So these are kind of, if we drop our notion of the isotropy in space and time, both space and time, because there is a rotation. Time is involved in only rotation, and in space only the space part. So if we are prepared to drop our notion of homogeneity, we shall have an acceleration. So we talked about the geodesic motion. We said that, Soumitra also talked about that in the morning, that if there is only gravity, there is no concept of any force in this general relativity. The particle will move along a geodesic, there is no force. Geodesic is the shortest, actually an extremum path between two given points. Anyway, but if there are non-gravitational forces, such as some pressure gradient, then there could be some acceleration. So it all arises out of the inhomogeneity in space-time. So acceleration can also give rise to some departure from the high degree of symmetry that we have assumed. So now, again, there is some tensor equation. Again, you don't have to look at it very seriously. The idea is, out of this velocity vector and its derivatives, we can write down an equation. So this equation, theta comma mu v mu, is the celebrated Raychaudhuri equation. I just tell you how you can arrive at that. If you have a quantity and you have a successive partial derivative of that, let's say you have some f and differentiate is a function of x and y. You differentiate it partially with respect to x and y successively, and do the other way around, first y and then x. These two will commute. But in tensorial differentiation, they would not. From the commutator, from the difference between these two, I mean, first you differentiate with x alpha and then x beta, and then do the other way around, with respect to beta first, then alpha. Then from the difference of that, you can arrive at a geometric quantity called the Riemann tensor, Anyway, they are all, I mean, you don't have to bother about it very much. You can arrive at this equation, which is the Raychaudhuri equation. The first term is basically the expansion, theta comma mu. So this is basically theta dot. That is the rate of change of the expansion scalar, the second rate of change of the volume. And then you have the acceleration term, its divergence. Then you have, again, the theta square. Then you have the acceleration is, again, due to departure from the homogeneity. And sigma square is from the departure of isotropy. Omega square is from the departure, from the existence of rotation in the space-time. Is equal to some geometrical object, r mu nu. And this is the Raychaudhuri equation. An important point to note. So until now, we have not used any general relativity. But as Pankaj mentioned in the previous talk, the right-hand side will give you the matter content through general relativity. Up till now, there is no general relativity. It's only a geometric object. So now if you use Einstein's equation, G mu nu is equal to T mu nu, or G alpha beta is equal to T alpha beta, A minus 8 pi G T alpha beta, for a perfect fluid distribution. This velocity vector is technical things, but for the sake of completeness, I have written that for a perfect fluid distribution, the velocity vector is an eigenvector of the Ricci tensor, this R alpha beta, and the right-hand side of Raychaudhuri equation will become minus 4 pi G rho plus 3p. The same thing that you had for the Friedman metric for the perfect symmetry assumptions of homogeneity and isotropy. So you can see that, so this equation, if you write down, if you replace the geometric term with the help of density and pressure, the equation will be somewhat like this. Theta dot plus 1/3 theta square is equal to minus of this object, which is matter, rho plus, it should be rho plus 3p. I have a print typo here, rho plus 3p, plus a mu semicolon mu, which is the acceleration term arising out of the absence of homogeneity, minus 2 sigma square, where 2 sigma is the shear and omega is the rotation. Now here a dot represents a differentiation with respect to the time, proper time. A is the measure of the linear dimension, the average scale factor of the left-hand side. And the left-hand side, theta dot plus 1/3 theta square combined will give you 3a double dot by a. Now you can recall that we had the relation 3a double dot by a is equal to minus 4 pi g into rho plus 3p in case of the homogeneous and isotropic model, which is called the Friedman model. But here we have more things. So you see that, so the left-hand side will become 3a double dot by a, but sign will depend on the other side, other things on the right-hand side. The matter part, as usual, mind you, there is a typo. There should be a rho plus 3p instead of rho plus p, but that contributes negatively. Sigma square also contributes negatively. So if there is any escape from the singularity, you need to have the help of either rotation, which gives you a positive sign. So minus 2 minus omega square, so this will give you a positive contribution. And also, depending on the signature that you can arrive at from the acceleration term, you can have a positive sign. So that can give rise to an escape from the singularity. 5 minutes only. Okay, I shall try to be. So, yeah. So the original version of the equation, Raychaudhuri equation, looked like this. I am coming, so give me 5 minutes more.
Sure, absolutely.
So I'm trying to be slow. Yeah. So this is the original version of Raychaudhuri equation, where he did not have any acceleration term, you can see, no inhomogeneity. Because of the simple reason AKR was interested in the geodesic motion, only gravity. So he did not include the acceleration term. But otherwise, everything is there. He included lambda as well, because some lambda was introduced by Einstein at some point of time in order to have a static universe. And Raychaudhuri did not start from where we indicated, from the commutator of the successive covariant derivatives, but he started from one of the Einstein's equations to arrive at this. But 2 years later in a paper, he indicated that you can arrive at this equation from the commutator of the successive derivatives of the velocity vector in 1957. This paper was published in 1955. So inclusion of acceleration, the way that I wrote the Raychaudhuri equation in the beginning was due to Jürgen Ehlers. The main contribution is that inclusion of acceleration, more general form of matter distribution. If the matter is, pressure particularly is inhomogeneous, you can have this acceleration. So Raychaudhuri was interested, this I told, is interested in geodesic motion. So he did not consider acceleration. So this I shall very quickly mention, I shall skip something. There are some examples in the literature of singularity-free solutions in cosmology. One is that of Gödel, which has no pressure, only density, and it has a rotation. But it has, mind you, Raychaudhuri equation indicated to you that you can use rotation to arrive at a singularity-free thing. A double dot can be positive. So Gödel utilizes that and arrive at a singularity-free solution. It has some bad things. It has bad things in the sense that it has closed time-like lines. You can go back in the past. If you can go back in the past, then you lose causality and lose all the requirement of any physics for that matter. And the other example was by Jose Senovia, which was talked about by Pankaj some time back. Senovia utilized inhomogeneity. His solution was a cylindrically symmetric solution. Our universe is not cylindrically symmetric. But anyway, it was a good example that as an academic exercise, in the realm of general relativity, we can arrive at a non-singular solution. But you see, he arrives at that from the acceleration vector, from inhomogeneity, right? And so it also indicated by Raychaudhuri equation. I shall make one quick comment about this Senovilla's thing, a Senovilla's solution. It was a nice solution, but it was shown that if you take the space-time average of the scalars like density, pressure, and other things, they all will be zero. And that was also shown by AKR in 1998 as a young man of 75 years. It was published in Physical Revulators. And it was done all alone. All the calculations and everything. We helped only in proofreading of the paper. So I shall skip this. I shall just make a comment that this is also possible. So whatever we have discussed is the Raychaudhuri equation for a material particle with a mass, but you can write down these equations for photons, for a null particle as well. It was done by, some time back, but I shall not get into that. Sachs and other friends. So I shall just talk about some modern assessments of Raychaudhuri equation. Just a few quotations. George Ellis said that it is the fundamental equation of gravitational attraction. This is the fundamental equation of gravitational attraction. What equation? Raychaudhuri equation. Jürgen Ehlers said this, the reviewed paper, meaning this relativistic cosmology where this equation was published. Here is truly a landmark in cosmology. It showed how results are in principle observable and local variables can be obtained without imposition of isometries. It can be considered as a forerunner of a program begun by Christian and Sachs, and continued by G. Ellis and his co-workers. Moreover, it paved the way to Penrose-Hawking singularity theorems. Okay. And this is by John Ehrman. Further evidence, that is regarding the singularity, was introduced in 1955 that in the cosmological context at least, singularities in general relativistic spacetimes are not artifacts of symmetry assumption. The evidence came not from one of the havens of the general relativity in America or Europe, but from Calcutta. In 1953, Raychaudhuri produced an analysis of cosmological singularities that was to have a profound effect on later developments, but it ran into difficulties with referees. The paper did not appear in 1955. So I had something about the Hawking-Penrose energy theorem, but I shall skip that. But I shall better talk about the history of the publication of the paper a bit. Because Soumitra and Pankaj dealt with that a bit, about the Penrose-Hawking energy theorem, Penrose-Hawking singularity theorem, how Raychaudhuri, it all started from Raychaudhuri equation. That is the important thing. But I shall better talk about the history of the publication of the paper. Aker had been working all alone in those days. He was working as a lecturer at Ashutosh College in Calcutta. In 1953, he joined IACS, Indian Association for the Cultivation of Science, and his expectation was that he would have enough time for his work. But the reality was somewhat different. He was asked by the director to work on solid-state physics, and then he was asked to work on quantum chemistry. They are both nice. No objection against them, but it was not to his likings. But incidentally, he did both. And he extended Coulson's work on free electron network approximation for pure metals. And Coulson's idea was that it would not work for alloys. Aker showed that it would work for alloys as well. Coulson himself appreciated the work. And not only compulsion of doing something not of his interest, at the same point of time, he was asked to sit in a small room which was erstwhile used as a kitchen. And I have heard this is true, but I have heard the story that one day he was working in the evening, then some of the research scholars asked him to move out because they will cook there. But his interest in the relativistic cosmology never abated. The first version of the paper, which included some speculative part as well, was sent to Physical Review D as a letter to the editor in April 1953. The title of the paper was Local Temporal Behavior of a Gravitating System in General Relativity. So it was promptly rejected. The summary of the referee's comment was that he could not understand where does the equation come from. And then he removed the speculative part, renamed it as Relativistic Cosmology 1, and sent it to Physical Review as a regular paper in December 1953. There was no response from the journal in spite of several queries from the author. After about a year, he sent the paper to Zeitschrift für Physik, and prompt came the rejection, thankfully so, from the editor saying that the results had hardly had any impact. Because I said fortunately so, because in 1955 the editor of Physical Review wrote that he could finally recover the report from the referee who recommended publication. So this was the short history of the publication of the paper. So I have used some resources such as the history of the publication of the paper can be found in the exchange of letters between John Ehrman and AKR in 1955. It was published in Ehrman's book, but the history of his days of his relentless fight can be found in AKR's diary. And both are included in anthology of various writings of AKR. Atto-Jigyasa is in Bangla mostly, but some diaries are in English, edited by his younger daughter, Parangoma Sen. Normally I would stop here, but I would like to say about one or two anecdotes if you allow. One is, Palash Pal in the morning said that, he was asked the question by some of the students that in those days, what was the style of asking questions for the teachers. So one of our great teachers in Presidency College would stop teaching if the students didn't ask any question. And another teacher would be a bit annoyed because he spoke very, very nicely, like a very picturesque description of everything. Because there was some kind of stopping him was kind of he thought that it's a hindrance to his lecture. AKR was kind of a balance of these two. He used to throw his points in such a way that one would be tempted to ask questions. I would give one such incidence, which was slightly in a lighter vein rather than a very serious type of thing. So a simple black hole, Schwarzschild black hole, we know that there is characterized by an event horizon. A slightly more complicated black hole, where there is no spherical symmetry, but there is an axial symmetry, is characterized by two surfaces. One is called the event horizon, from which nothing can escape, and the other is called the static limit. And the region between the static limit and the event horizon is called the ergosphere, and one can extract something out of that. So Penrose devised a process, theoretically. He said that if a particle moves into the ergosphere, and it breaks into two parts, one part will get into the event horizon, so it will not come back. So it forms a part of the bound system, it will have negative energy, right? So to conserve energy, the other part will have enhanced energy and come back. So this was basically the process. So Penrose said that in this way he can solve two important problems of the world, of the earth, at one go. One is the problem of energy and that of the garbage. If we can if our engineering is such that AKR is describing this in this way. If our engineering is such that we make an aircraft and fill up one part of that with the garbage, and our engineering is such in the ergosphere, it breaks into two pieces, the garbage gets into the event horizon and the other part comes back with the enhanced energy. So we solve two problems. So promptly one student gets up and says, what happens if the garbage comes back? So AKR was waiting for this. He was talking in such a manner that one has to ask this question. He said, I said, if our engineering is such, you are a very bad engineer. So the other thing is that it's not an anecdote I would like to share with all. So with all this, you may think that he was a very absent-minded professor. He was not at all. He was not at all an absent-minded professor. So we attended his classes in Kolkata, in Presidency College, and then in MSc again in Presidency College. The Calcutta is very hot and humid. People from Madras will well appreciate that, what hot and humid would mean. So he used to wear a dhoti and used to have his dhoti end, what we called kucha, in his left hand. And in those days in Presidency College, we had cloth dusters. So he used to clean the board with the cloth duster and wipe his face with the dhoti end, kucha. We waited for 5 years, but we never saw him doing the other way around. He never wiped his face with the duster and cleaned the board with the dhoti end. Thank you very much.
Thank you, Narayan, for a wonderful lecture. The floor is open for questions. Questions? Yeah, sure, please. There.
Yeah, thank you, Narayan, for this nice lecture. Just a comment. We celebrated, the 50 years of Raychaudhuri equation, organized a meeting at Ayuka. Yeah. And naturally, I asked for his permission. I was the organizer. So he says, oh, what do you mean? I mean, this shows his kind of spirit. He says, you can celebrate a person or, he becomes 60, 70 or whatever, but you don't, do a conference for an equation. But then finally he said, okay, I mean, that can be done. And he himself also gave a talk. This proceedings of this meeting are available, published by IUCA and later by also Indian Academy of Sciences. Yes, and also you are right. I mean, he always wore a dhoti. I have not seen him in kurta pajama, which was Professor Vaidya's regular attire. But the sort of his way of talking and what you said, his teaching style, it was always filled with a lot of energy. Thank you very much.
Thank you. Thank you, Pankaj. Any other comments or questions?
Questions, particularly from the students, if any, I would be glad to answer. Try to answer, rather.
Anyone? I have a simple, naive question.
Please.
Is the Raychaudhuri equation an identity?
Yes, I should have mentioned that. Raychaudhuri equation is actually an identity of Riemannian geometry. It's an identity with zero dynamical content. It's an identity of Riemannian geometry. You don't need any general relativity for that.
Okay, thank you. Yes.
Yes. Polazda.
Vorticity tensor and shear tensor, those have some analogous with fluid mechanics, right?
Sorry?
That vorticity tensor and shear tensor, how did they actually came? It has some analogous with the fluid flow, or
Absolutely, absolutely. We are talking about geometry. We're talking about the velocity vector, velocity of the geodesic, right? But yeah, so suppose you have a fluid, for fluid you have the state analogy. If you have a fluid and if you have a velocity vector, the curl of the velocity will give you the rotation, omega, you know. So it's the same. So in the matrix, the symmetric part will, trace-free symmetric part will give you the shear, the anisotropy in space, and the antisymmetric part will give you the rotation, the vorticity.
the same equation can be used in some fluid mechanics or plasma?
Absolutely.
An analogous
In fact,
equation.
I'm not sure. So you are attending the conference from the beginning, right?
Yeah.
So Shayan in fact mentioned about that.
Yes.
So those are more technical, so I did not bother to talk about that today. Yeah. So you had another question.
Did you have another question? No. Are there any other questions? Yeah, Professor Pal.
Narayan, you said that, I mean, just give a yes-no answer to my question. You said that the director of cultivation wanted him to work in quantum chemistry and these things, right? Did you conceal the name of the director intentionally? Yes, no?
Well, yes, I would say.
I didn't ask for the name.
Any further comments, questions? Okay, if there are no further questions, let's thank Narayan again. As Narayan had done, I think we should take another opportunity to thank the organizers, Dheeraj, Manjari, Arnab, and Ravi, of course, and of course, IMSC for wonderful venue and hospitality. Thank you.